Hello everyone and welcome back to another video. In the last video we talked about processes and we went pretty deep into processes. So in this video we are going to talk about devices and we are going to talk about file systems. We are going to understand what devices and file systems are. Now this video is a part of the Linux Masterclass course. So if you are new into this course, if you are watching this video or my channel for the first time, then I'd recommend that you start from the very beginning. It is going to make you comfortable with Linux, and the link to the playlist would be in the description below, so do make sure to check that out. And without any further ado, let's get started. Now when you connect any device to your machine, it needs some device drivers to function properly. And these device drivers, to interact with them, you need some device files, right? So these device files are like inside the slash dev directory, right? And let's quickly check out what's there in the slash dev directory. So I'll simply do an ls, which is the list command, and then slash dev to check out what is there in this directory. And I'll see that there are a lot of directories in front of me, right? So here if you'll notice, then there is one directory known as null. Now if you remember from the second lecture, we used the slash dev slash null directory, which is right here, and we used this directory to sort of nullify the error that we were getting, right? We didn't wanted the error to get printed in the console, but we wanted, nothing to happen, and if in case we get an error, and we did it through the to and then greater than command, right? So to quickly show you an example again, just to recall, I can simply do an lg, and then after lg I'll do a 2 and then greater than symbol and then slash dev slash null, right? I press enter and I can see that nothing happens, but if I remove this entire thing and then do an lg, it says lg command not found. So what happened to this error? It simply went to the slash dev slash null, and this means that we don't want, we want this error to, just go in the trash. We don't want anything to happen as such if we, let's say, get an error, right? So we have already used this directory. Now we see a lot of data in front of us. When we try to list down what is there in the slash dev directory, we see a lot of data in front of us. So let's quickly do an ls hyphen l on this directory and see, what type of things do we get out of it, right? So we can see that it again gives us, a very elaborate list of, data. It shows us all the contents of that directory along with, different things. But this entire thing kind of looks different than, what we have seen so far when we, let's say, try to do the ls hyphen l in a normal directory. For example, if I, let's say, do an ls hyphen l uh, in currently where I am in my home directory, then I can see that, this is pretty different than what I see above. It shows these weird numbers and, things like that. So what is all this, right? So let's quickly, try to understand what all it is trying to show us, right? And for that we'll go back to our you know good old Xkelly draw, right? So the first thing that we see in front of us is again what? It's the permissions, right? So the first thing that we see are the permissions, right? And permissions are again, represented by this, 10 bit stuff, right? So these are the permissions that are there. Then we see the owner and the group, right? So we see the owner, and don't worry about this number that we see here, right? Don't worry about this number per se. We are going to talk, in depth about what this number means later on, but for now, right, ignoring that number, we have the owner, we have the group, right? Now coming back here, we see these two numbers, right, separated by comma. Some of them has a numbers, like the first just one number, some of them has two numbers, right? So let's talk about an example which has two numbers. The first number that is there, it is the major device number, right? And the second number that is there, the 235 in the case that is highlighted, it is the minor device number. Right, so we have that, and next to that we have some timestamp, and next to that we have the device itself. Right, so we have the timestamp, and we have the device itself, or you could say the device name. Right, like what kind of device is it. Right, and all of this are the contents of the slash dev directory. Right, so this is what it is. Now let's first try to understand the permissions that we see. Now we know in the permissions that the first bit is usually the type of, whatever we are seeing. It could be a file, device in this cases, and things like that, right? And we know that if the first bit itself is a D, then it is a directory, a simple directory, right? We know that if this first bit is a simple dash or a hyphen, then it is a regular file, right? But we see, and we also talked about if it is an L, then it is a link, right? Some sort of a link, right? But we also see a lot of different characters here, like there is the C character, which we don't know what it means, right? There is this B character, which again we don't know what it means. So let's try to understand what these characters are now, right? So if we talk about the type characters that we see, right, we know that a D is a directory, right? We know a hyphen is simply a file, we know an L is simply a link, right? Now what does a C mean? C simply stands for a character. Now we saw something called a B, right? We saw a B character, right? So B simply means block. Then there is one character known as a P, right? This stands for what? This stands for pipe. And we have already seen what pipe is. Pipe is represented by this symbol, which is backslash, shift and backslash, so you get a pipe. And this simply transfers the output of one command, and it feeds it as an input to some other command, right? So we already know what the pipe means. And we have another character, which is an S, right, which stands for a simple socket, right? So we have all these characters. Now we don't have to talk about directory, file and link, but what are these, like the C, B, P, S? What are these these characters, like what types are these and what do they mean? C, whenever it is a C, right, when we talk about a C, C simply means a character device, right? So I'll just scroll down a bit. So C simply means a character device, and this means that it transfers data but one character at a time, right? So it will only transfer like all the data but character by character, right? And we know deep down everything is just every piece of information or everything is just some bits that are there, right? So it transfer that data character by character, right? So this is the character device that we have. Now similar to this we have a B, which is for block device. Now these block devices transfer data in large fixed sized blocks, right? So anything that is transferring data in big sized blocks, things like our hard disk, our SSD, all of these are block devices, right? So I'll also write down examples like the HHD that we have, the hard disk, right, or the SSD that we have nowadays, right, etc. right? All of these are block devices, right? And we had a P, which simply stands for pipe. Now we already know what this is, so it simply allows two or more processes to communicate with each other, and instead of sending the output to the device itself, it kind of sends the output some other process. And then we finally have the S, right, which stands for socket. Now these socket devices, they kind of facilitate communication between processes as well, just like the pipe device does, but they can communicate with multiple processes at once. So that's all about the permission bit, right? Now we understand what the permission bit is, and the rest of it is same. Rest of it is going to be generally the R, W and X, and it simply represents the permissions of the users, the permissions of the groups, and the permissions of the any other user that is there. The first bit is about the owner's permission, then the group, and then any other user that is there, right? So we already understand the permission bit. We know what owner and groups are, no need to discuss that again, right? And let's talk about the major device number and the minor device number, what that actually means. These major device number and the minor device number that we have, right, this and this, they are usually done for device characterization, and this major device number represents the device drivers that are being used by the device, right? So in this case we can say that this auto fs device, whatever it is, right, it is using a device driver which might be represented by a 10, right? And this btrfs control, whatever it is also using the same device drivers that are being used by AutoFS, right? So this means that they are using the same device drivers. Now this minor device number simply tells the kernel what unique device it is, right? So there could be two devices of same type connected to the system, right? And both of them, since they are similar, they might be using the same drivers, but the kernel needs something to identify those devices, right? Like which device is which one. So this minor device number is simply used to differentiate between similar devices. Now just to show you an example, in my system right now I have two NVMEs connected to it, 500 GB each, right? One of them runs Windows and the other one runs Linux, right? So I have two NVMEs connected into this system right now, and you can see that here you will notice that the NVMe that I have, there are two NVMEs, right? So the first is this one, NVMe 0 and 1. Let's write this down, right? So my first NVMe is simply NVMe 0 and 1, right? And I have another NVMe which is NVMe 1 and 1, right? So I have another NVMe NVMe 1 and 1. So if you will notice, then both of these NVMEs, like this NVMe, this one, the NVMe 0 and 1, and this one NVMe 1 and 1, they both have the major number as 259. Simple reason being that they are using the same drivers, right? But their secondary numbers are different. It says 0 and then 1 and then 2 and then 3 and then 4 here, and then it says 5 and then 6 and then 7 here, right? So it simply means that all of them except for this 241 here, except for this one, all of them here are simply using the same drivers, but they are identified through these minor device numbers, right? So that is there, and we now see that after this we have these four different things, NVMe 0 and 1, and then P1, P2, P3, P4. So these simply represent the partitions of the the NVMe that I have in my system, right? So if you take a look at the first one, right, it as a parent, it has NVMe 0 and 1 P1, right? And then continuing this, it has up till NVMe 0 and 1 P4. Right, so it has all these partitions P1, P2, P3, P4. Right, and similarly the second one that I have, NVMe, right, it has just two partitions, right, P1 and P2. Right, so it again simply has just two partitions, NVMe, and then 1 and 1, because this is the partition of this one, right, and then P1, and the second one is NVMe 1 and 1 P2. Right, so these are the two partitions of my second NVMe, and the first NVMe that I have has four partitions. Right, so these are simply partitions of first NVMe, right, which is 0 and 1 in this case, right, and these are simply partitions of second NVMe, which is 1 and 1 in this case. Right, and you will also notice that the name up until this is going to be same for all the partitions, which is going to be same as the NVMe that it is. Same goes for here as well. Right, this and this are going to be same, which is going to be the same as the name of the NVMe that is there, and then the partitions are simply P1, P2, P3, P4 and P1, P2 here, and that is the reason why their secondary number here, if you will see, the first main NVMe that I have is using the same drivers but has a second minor device number as 0, then its first partition as 1, second 2, third 3, then 4, and then my second NVMe, although it's using the same device drivers 259, right, it is represented uniquely for the kernel as 5, then this is represented as 6, and then this is represented as 7. Right, so this is how the kernel differentiates, like the devices are of same type, but which one is it dealing with exactly. Right, so that's what this is usually for. We also have some pseudo devices connected in the system. Right, pseudo devices are those devices that are not physically connected with the system. So the NVMe's that we are talking about, they are there like connected in the motherboard of my computer, right, but there might be devices that are not physically connected with the system, right, devices like slash dev slash null, right, or there is one device called slash dev slash 0, right, or there is one device called slash dev slash random. Right, so all these devices that we are talking about, they are not physically connected with the system, right, but and since they are not physically connected with the system, they are known as pseudo devices. Right, they still have some utilities, like as we talked about null simply just vanishes whatever you want, whatever goes into it, it's like a black hole of computer system, right, never comes back. Right, and slash dev slash random is simply used to generate a random number, things like that. Right, so and again, I mean, these pseudo devices, all these three pseudo devices are character devices. Right, so they transfer data one character at a time. Right, so they are character devices. Now there is another directory known as the slash sys directory. Right, so there is another directory known as the slash sys directory. Right, just like we had the slash dev directory, and this directory simply gives a more detailed information about the slash dev directory. Now both the sys and dev directory that are there, they are majorly similar or mostly similar to a lot of extent, but they still have some major differences. The dev directory allows programs to access devices. The sys directory is used to view information and manage devices. Right, so that is the major difference, and this sys directory is also kind of known as a file system. Now this sys directory contains all the information about all the devices that are, there in the system. Things like, the model of the device, the manufacturer of the device, where the device is plugged in the system, what is the state of the device, even the hierarchy of devices, etc. Right. So we can check what is there in the sys directory, right? I'll simply do a ls and then slash sys. Right, I press enter and I can see that there are a lot of things coming up for block and bus and class and dev and devices and firmware and fs, which is short for file systems, things like that. If I, let's say, do an ls and then slash sys and then slash devices, right, I press enter, I can see that there are all these things that are there. If I simply do a slash sys slash dev, I can see that it asks me which one do I want to see. I can go to block and here I can see that all of these uh, blue things, all of these things are coming in blue, and blue simply means that they are links. If I do ls hyphen l here, then I will see that all of them are represented by an l, right, which simply means link. We are going to learn about links later on, right? But for now, if we again take a look at this, then we can see that it has a very simple notation, right? Simple notation, like it is first representing the major device number that is there, followed by a colon. Right, so it first represents the major device number followed by a colon and then the minor device number, right? So in this directory's case, it is representing that it is using the device driver 259, and it has the minor device number of 2, right? So if we again take a look at slash dev directory here, sorry, forgot the hyphen l, then that directory there was simply representing this, right, NVMe 0 and 1 P2. So 259 colon 2, right? This is all the information about it is stored in here, right? um, in here, right, in this link per se, right? So this is what it usually is, and again we can check a lot of things here, like if I, let's say, go to one of those directories, right, here I'll go into dev and then block means that all of these are block devices, right? And inside block I say that I want to go into 590, right? I press enter and I can see that inside of it I have a lot of things, like I have information about all the partitions that are there inside of that, because this 0 simply means, like, if you remember, then 0 is simply the first NVMe that I've connected, and inside of that we have 4 partitions, right? So it contains information about all the partitions that are there, NVMe 0 and 1 P2, right? And about its power, its queue and trace, and things like that. So it contains a lot of information about the entire thing. So from here you can manage the devices, the system manages the devices, and yeah, so that's pretty much it. Now we have talked a lot about devices. Now let's move to the more important topic of this video, which is file systems, right? So the first thing that we should do is, like, just to understand the entire file systems, let's take a look at the hierarchy of how things goes. So I'm simply going to do an ls and then hyphen l and then a slash, right? Slash is my root directory, right? So let's just check out all the components of the root directory. I press enter, I see that a lot of things that are there, yeah, right? So all of these things are there that you know generally are inside the root directory, and everything starts from here, right? So let's try to understand all of these directories one by one, right? So here again we are talking about file system, and file system I'm going to write as fs from now on, right? And we are talking about its hierarchy. Now the first directory that we, what like we should start talking about is the slash itself, right? Which is the root directory. Everything starts from here, right? So it's like the root of the entire tree of the file system hierarchy that is there beneath it. Everything starts from here, right? So the second thing that is there is the bin directory that we have here, right? This bin directory, right? So if we talk about the bin directory that is there, these are just it simply contains essential and ready to run binaries that are there, and it also contains binaries for some of the most common commands that we use, such as ls and cp and mkdir and things like that, right? So it contains just binaries, right? Bin stands for binaries, right? The next directory that we have in front of us is the boot directory, right? The boot directory. Now this boot directory simply contains the bootloader files that are used by kernel, right? So it simply contains some bootloader files. Then next, what we have with us is some boot info and some boot sav. Again, I mean, this is something that we can skip, right? We have a cd-rom, again something which is not essential. Now then we simply have the dev directory. So this is something that we just talked about, right? So the dev directory that is there simply contains the device files, right? The next thing that we have is the etc directory, right? The etc directory. Now this is the core system config directory, right? It contains all the configuration files of any program that you're running. Most of the programs that you run has some settings, some configurations that you can do to change the behavior of the program or something like that, right? So it contains all the config files, not binaries, right? So contains config files, right? Then after the etc we have the home, right? Something that we already know about by now. This is simply personal directories for different users, no need to write that. Then next to that we have the lib directory, right? And different variants of lib directory for different types of programs, right? So we have the lib directory. This usually contains the library files that the binaries can use, right? So the binaries might be needing some libraries, some external libraries to execute their code. And don't worry if you don't yet understand what external code might mean or what libraries might mean, right? But we will understand about all of that later on, not in the Linux Masterclass, but in the web development course, when we move forward to, let's say, Python or JavaScript and things like that, then we are going to obviously discuss about what these libraries are, and it's going to make a lot more sense then, because you'll be creating your own libraries, right? So it will all make sense. Don't worry about it right now. Then after the lib, we have a lost and found, pretty self-explanatory. We have a media. So we have a media. This is simply like an attachment point for any, USB or something that you might have connected to the system. So if, let's say, you connect a USB to the system, then this is, where it's going to get attached in the media directory, right? So that is media, again, not writing that. Then we have an mnt directory. We have an mnt. This is like the temporary mounted file system, right, like just the entire file system temporarily mounted into this directory /mnt, right. Then we have an opt, right, opt. This opt usually contains the optional applications software packages, right. So it's just optional software packages. And just to check, I can simply do a /opt and I'll see that there's a folder known as Google, right. Google is usually just the Google Chrome, right. So nothing to worry about. And then we have a directory called proc, right. We already know about proc as well. Process info, right, nothing more than that. Then next we have a directory called root. So this root directory is the home directory for root, right. So root also has a home directory, right, because ultimately it's a user, the most powerful user in the system, but it's still a user. So it has a home directory which is the /root. The next we have a run directory, right. So we have a run directory, and this simply contains information about the running system since it was booted, right. So when I started this system some time ago, then whatever information it has collected since then would be saved in this run directory, right. So again, I'm not going to write that. Then we have an sbin, right. So we have an sbin, and sbin directory are generally system binaries, right. So bin was just binaries, these are system binaries. They can only be executed by root, so only the root can run these system binaries. Then we have a snap, we have an srv, again these are something that are not important as such. We have a swap file, like it's a regular file. And next we have sys is something again that we just talked about, right. It helps in managing all the devices and the file system, right. So sys, again we don't have to talk about this, right. Next we have a tmp, right. The name might be suggesting you something about it. So it's just like a storage for temporary files, right. Storage for temp files, that's tmp, right. And after that we have a /usr. These are usually the user installed softwares and utilities, right. And finally we have our last directory, which is the var. This is simply the variable directory. Any system logging or any user tracking, any caches or whatever it is, whatever is continuously changing is maintained in this variable directory, right. So since it is continuously changing, it is a variable and it is maintaining it in the variable directory, right. So this is generally the file system hierarchy, the hierarchy of the entire file system, that is starting from the root directory, Since we've been talking about file systems, let's also talk about the different implementations of file systems that are available out there. And there are a lot of implementations. Some are faster than the others. Some support a larger storage, etc., etc. Right? Different file systems have different ways of structuring their data. So the structure that we see in front of us when we, let's say, do the ls command on the root directory, this structure, it might be different for some other file system. Due to so many implementations available, different applications need some way to operate on different types of file systems. Like it's not sure what structure they might be having. So let's say that we have an application, right? We have an app, right? And let's say that we have a file system, right? So we have an application, we have a file system. Now this application needs to run on this file system, right? And it's not sure, if this application, the way it operates is it's going to support, like this file system is going to support this application. So it's not sure. Now there is an abstraction layer in different file systems that is there, and this abstraction layer is generally known as the virtual file system. So let's say that there is an abstraction layer here, right? Let's say this is an abstraction layer, and this is known as the virtual file system. Right. So now if let's say the application wants to operate on this file system, then what it will do is it will you know try to use this virtual file system, and now it's the job of this virtual file system to make sure that this file is operable on this file system, right? No matter whatever the structure of this file system is, it doesn't matter, just because there is an abstract virtual file systems layer in the middle that is going to help the application operate on this file system. Now you can have different file systems in your system depending on how you have created the partition. In my example, as I have already shown you, I have two NVMEs in my system, and I used one NVMe entirely to have the Windows operating system, and I have one NVMe entirely to have the Ubuntu operating system that I'm using right now. And you could do it in the same disk as well by creating some partitions. I also have some partitions created, but I mean all those partitions belong to just one operating system in my case. In some other cases, what happens is that people create partitions, and one partition is Windows based, the other one is Linux based, and things like that. So that can also be done, but we'll talk about it in a bit more detail later on in this video. Before we talk about that, let's discuss a situation where let's say you have a very large file, right? And you're copying this large file from one place to another, but while copying this, and since it is a large file, it's going to take a lot of time to just copy from one place to another. So let's say that you're copying this file, and while doing that, your the electricity goes out, your system shuts down, something happens, right? So your system shut down, and this large file that you were trying to copy, it suddenly became corrupted, right? So this leads to some inconsistency in your file system. Your file system would be inconsistent, and it has corrupted files and things like that, right? Now when you boot it back up, right, when you again start your system, your system might perform some file system checks just to make sure that everything is okay. Now you must have noticed that especially if you have used Windows, you must have noticed that if let's say your system shuts down unexpectedly, then sometimes when you start your system, it kind of takes some time to just run some checks, right? And this entire thing might take a lot of time. It might take a lot of time depending on how big your file system was, right? if your file system is really huge, like GBs and TBs of data, then it's going to take a lot of time just to make sure that everything is okay. Now to avoid this problem, there is a system known as journaling. Right. So just to avoid this entire situation that I am talking about, there is a system known as journaling, and journaling is a part of majority of the operating systems and file systems that come these days. With this, before your system even begins to copy a file, it will write down what you are trying to do in some log file, and this log file that it writes it down in is known as a journal. Now once the task is completed, once it has successfully copied whatever you are trying to do, right, once the task is completed, it will simply mark that task as completed in the journal. Now with this, your file system remains consistent, and if in case your system suddenly shuts down, if it just powers off suddenly, just in the situation as how I explained, what would happen is that your system would know exactly what it was trying to do before powering off. Now this time it will only have to check the journal instead of checking the entire file system, like what went wrong and what are the files that are corrupt. It will only check the journal, see what are the tasks that were not completed, right, and it will just know what exactly happened, and because of that the boot up would be much faster. So let's talk about some of the most common desktop file system types that are out there, right? So let's talk about some desktop file system types. The first one is ext4. Now you must have heard these names somewhere or the other, right? So this ext4 that is there, this is one of the most latest versions of the Linux file system, and it is also compatible with the previous file systems, the ext2, ext3. Now this ext4 supports disk space of up to 1 exabyte. It also supports file size of up to 16 terabytes, right? So file size that it supports is up to 16 terabytes. And just if you don't know what an exabyte is, right, just for like your reference, we know that 8 bits is 1 byte. Then we know that 1024 bytes is 1 KB, kilobyte, right? 1024 KB is 1 MB, megabyte, right? 1024 of MB is what? 1 GB, gigabyte, right? 1024 GB is what? 1 terabyte, 1 TB. Now this 1024 TB is what? 1 petabyte, PB, right? Petabyte. Now this 1024 petabyte equals 1 exabyte or 1 EB, right? And after exabyte there is simply zettabyte, there is yottabyte, there is brontobyte, and there is geobyte, right? So, and geobyte I think is the largest size that is there, but it's kind of huge, right? I mean currently the common size that we use is TB, right? So this is quite huge, right? So yeah, I mean this is how the usual breakdown is. So this ext4 supports the disk size of 1 exabyte and a file size of up to 16 terabytes, right? So the disk space that you have in an ext4 system could be up to 1 exabyte, but any file that is there could not be larger than 16 terabytes, right? So these are the general features of ext4, and this ext4 is the standard choice for a Linux file system, right? So that is there. The second one that we have, right, is something known as a btrfs, right, or also known as butter or better, any of the two, file system, right? This is the most this is the more latest version of Linux file systems. Now this is the new file system for Linux, and it comes with a lot of things. It comes with the snapshots and incremental backups, performances, and much more. But the problem is that it's not yet compatible, and it's not yet stable, right? So these are the problems with this file system. So I mean, it's still relatively new, but it has some features that are not there in the previous file system, or optimized features, right? Optimized from the previous file system. The next one that we have, the third one, is the XFS file system. Now this XFS that is there, this is a high performance journaling file system, right? So it does, like, it manages all the journaling, and it's a very like high performance file system. It is generally good for servers that host media or something. So if you're talking about YouTube, on which you are watching this video, on which this video is hosted, YouTube's might be using a file system for their servers that is XFS, because it is very good for large files and media servers, right? And since YouTube hosts a lot of media, then it might be that they must be using XFS file system, right? Because it does the journaling for you, and as we know, the benefits of journaling, if your system, let's say, suddenly shuts down, then since yours if we talk about a media server, since it's going to host a lot of data inside of it, then just to check the file system, just to go through the entire file system might be a very time consuming task, right? So I mean, that's where journaling is something that we need, right? We heavily need, because if in case the system shuts down unexpectedly and some data was transferring from one place to another, then it might get corrupted, and the system needs to know as soon as possible what was it doing before the catastrophe happened, right? So that is the XFS file system, the third file system that is there. Then the next file system that we have is the NTFS and the FAT file system. So you can say NTFS and FAT. This is usually the Windows. Might have, like, you must be very familiar with this if you have been a Windows user, right? Whenever you try to format your pen drive, it asks you, do you want to do it in NTFS, AXT4, things like that, right? And then lastly, we have the HFS plus. HFS plus. This is the Mac file system, right? Simply for Macintosh, right? So these are the general file systems that are there. Now to check the file system that you are using in your system, there is a simple command that you can do. I'll quickly clear this. I can simply do a df and then -t, right? T is going to be capital. I press enter, and it is going to show me a list of whatever I'm using. So here you would see that in my second one, it says that my /dev /nvme nvme1 n1p1, right? Which is my second NVMe, is using ext4 types file system, right? So it's using this file system, and this is the Linux file system, right? And then it says then that in my /dev /nvme0 n1p1, which is my first NVMe in which I've installed Windows, it says that I'm using VFAT, right? VFAT. So FAT is again like for Windows, as we saw NTFS and FAT, right? So this means that in my first NVMe I'm using Windows and my second NVMe is using Linux, right? And again it has some data along with it, 1k blocks, like how many 1k blocks are there in this, how many 1k blocks are there in this, right? How many out of them are used, right? How many out of them are available, right? And what percentage has been used out of it, right? So percentage of usage, right? So it shows you all of this useful data, and you can quickly check what file system are you using in your system right now. Now we know that all the hard disk and SSDs that we have in our system, they are block devices, right? Even when we were checking the /sys directory earlier, we saw that all those things were inside the block directory, right? So we know that these are block devices that are there, and now inside of these block directories we can create partitions, right? I already showed you a lot of partitions that I have in my system. So we can create these partitions. Now these partitions are useful to separate data. Like instead of having just one file system in your entire hard disk or SSD or NVMe in my case, right? So instead of having just one file system in your entire disk, you could create multiple partitions and have in you can create multiple partitions, and these partitions are going to act as individual block devices, right? And now then I mean you can have more than one file systems in different partitions. If let's say you have a SSD or a hard disk that is 1 TB in size, you might create two partitions, 500 GB each, right? And you might want to have Windows in one Windows file system in one partition and Linux file system in the other partition, right? So that's how you can have multiple file systems in the same disk through partitions. Now to check what all partitions you have created in your system, there is something known as partition tables. They generally tell you how a disk is partitioned, and it also tells you you know where does the partition begin, where does it end, which partitions are bootable, what sectors of the disk are allocated to a partition, etc. So it kind of tells you a lot of things. And there are two main partition schemes, right? So there are generally two main partition schemes. So two main partition schemes, right? The first one is the MBR. This is simply the master boot record. And the second one is the GPT. This is simply GUID partition table. Now we know that partitions helps us organize data, and we can have more than one partition in a disk, but these partitions cannot overlap each other. And if let's say we have some space that is not a part of any partition, then that is generally known as free space, right? So just to show you an example, I can simply open a new program called disks, right? I open disks and I can see that I have these two disks. So the first disk, I can see that there are four partitions, right? This one partition is the file system partition, right? Then I have partition 2, right? And this is just the EFI system, like my file system. And this is Microsoft reserved for Windows, right? Then this is the partition where I have all the basic data. The size is 499 GB for this one, right? And then I have this Microsoft Windows recovery environment, right? So that is there, and then I have a free space of about 1.1 MB in my first NVMe, right? Then I have another NVMe 500 disk. Here you can see that the first sector, the first 250 GB of this this second NVMe that I have, this is empty. This is free space. I have not allocated it either to Ubuntu or to Windows, right? I have just kept it empty in my system. If in case I want to install some other operating system, later on in time, right? I might want to go to Arch Linux or something like that. So for that I have kept some free space, right? You can also see that then I have my NVMe 1 and 1 P2, right, which is 1 MB of reserved space for most probably for booting my system, right. And then I have this 250 GB of file system in my NVMe N1 NVMe 1 and 1 P1, right. This is the Linux file system where everything, all my data is, right. And then I again have some free and free unallocated space of 1.1 MB, right. So I mean, this is how usually the partition goes, right? Now, if we talk about MBR here, right? So this is usually the traditional partition table, and this used to be the standard early on in time. Now, it supports disk up to 2 TB, right? So if your disk size is up to 2 DB, then it can definitely be supported by the MBR partition table. Now the problem with this is that it has a limit of just 4 partitions, right. So it can only have 4 partitions, and these 4 partitions that I'm talking about are are known as primary partitions, right. So it can only have 4 primary partitions. But this is very annoying, right? I mean, it might be that you want to create more partitions. So how would you be able to do that? So out of these 4 partitions, 4 primary partitions that you have, you can just take one partition, right? You can just take one partition out of it, and you can make it an extended partition. Right. So you can at max have 4 primary partitions, but out of these 4 you can just take one. Only one is allowed per disk, but you can take that one primary partition and make it an extended partition. Now this one extended partition that you have, this extended partition can then be divided into logical partitions. Right. So this extended partition can then be divided into logical partitions. You can have as many logical partitions as you want. Doesn't really matter. Now, one thing that is there is that all of these logical partitions that are there work exactly like primary partitions. Right. So this entire logic is kind of stupid, and why it is there in the first place is something that is beyond me. I mean, before shooting this video, I tried to, you know, uh, explore a little bit on the internet and some books, like why the hell does it, happens like this. But it's like no one has an explanation for this. It's just like this for some reason. You can have 4 primary partitions in a disk. Out of these 4, you can have like convert only one primary partition into an extended partition. This extended partition can have as many logical partitions as you want, and all of these logical partitions are going to simply behave as primary partitions. So let's move forward. Right. So let's now talk about GPT. This is becoming the new standard for disk partitioning, right? Whatever partitioning is done in today's time is done with the GPT partition table. Now unlike MBR, right, it has only one type of partition. It's not like there's a primary partition and then extended partition and then logical partition. There's only one type of partition. You can make as many as you want, right? No one is going to stop you with that. Now each of these partitions is going to have a globally unique ID, which is the GUID, right? This G in the name, right? This is the globally unique ID, right? So all of these partitions are going to have a globally unique ID, and this is usually used with the UEFI based booting. Right. So that's all about the GUI GPT, right? The GUID partition table. Now let's talk a little bit about the file system structure. So file system is basically just an organized collection of files and directories, right? It's like a database to manage the files and the actual files itself, right? So file structure has four components to it, right? Four major components to it. So we are going to talk about file system structure, right? And it has four components. The first component that is there, it's the boot block. Right, so first component is the boot block. It is located in the first few sectors of the file system, and it is not actually used by the file system, but it is used to boot the operating system, right? And each and every operating system just needs, one boot block, right? So that's the boot block. The second component that is there for any file system is the super block. Right, so the second component is the super block. It is a single block that comes after the boot block, and it generally contains some information about the file system itself. Information like size of the inode table, size of the file system, etc. Right, so it's just some information about the file system. Right, then we come to our third, component of a file system, and this is the inode table. Right, so it's the inode table. This inode table is just like a database that manages our files. Right, now each file or a directory has a unique, entry in the inode table, and it just contains information about the file. We are going to study about inodes in a lot more detail in this video, but let's move on to the fourth component for now. The fourth component that is there are the data blocks. Right, so we have the data blocks. These are like the actual data of the files and the directories, right? So to get into a little bit of more detail into the file system structure, there is a command that you can use, which is simply sudo parted -l, right? I press enter, enter my password, and then I can see that it kind of shows me, some informations about my partitions, right? So it says that I have my first NVMe with the model number, right? So this is my first NVMe, and it tells me the location as well as the size of the disk that is there, right? um, and then it tells me that this partition table is of GPT type, right? Something that we discussed just a while ago, right? And then it tells me about the partitions that are there. So it tells me that there is a partition that starts at 1049 KB, right? I told you that the first partition itself, like the first sector, is the boot block, right? So it tells me that it starts from 1049 KB and ends at about 106 MB. Right, and we also saw that there was 1.1 MB of free space. So after the free space, it's starting from 1049 KB. Right, so starting from 1049 KB, it ends at 106 MB. Its size is about 105 MB. The file system type is F8032. Right, and this is the name of the partition, EFI system partition, and it is for boot, right? It's simply, the flag that the system has given it is the boot, right? So that is there. Then from 106 to 123, about 16.8 MB is Microsoft reserved partition, right? Then from 123 MB to 500 GB, about 499 GB of data is the basic data partition, the data blocks that we were talking about. And then we have some 500 GB, to 500 GB, about 588 MB, right? This is hidden, right, for some purposes I'm not sure about, right? Then we talk about our second NVMe. This is the model of the second NVMe. This is the, the size as well as the location of the disk, NVMe 1 and 1, right? Then we know that this again follows the GPT partition table, right? And since I have 250 GB of free space in my second NVMe, it starts from 250 GB, ends at 250 GB with a size of about 1049 KB, which is about 1.1 MB. And this is used for my BIOS grub, which is my bootloader. So I am currently using grub as my bootloader for my system. Since I've dual booted, grub is like, it makes it a lot easier to just switch between Windows and Ubuntu whenever I want to. When I start my system, it asks me which operating system do I want to load from there. So it's taking about 1.1 MB of my space, and then 250 to 500 GB, about 250 GB is my ext4 file system, which is my data blocks, right? So this is how my system is partitioned right now. My two disks that are there, the two NVMEs that I have, are partitioned right now in my system. Now there are various disk partitioning tools that you can generally use, right? So the tools that are there, and you can read more about them on the internet. I'm not going to cover that in this video. Right, but the tools for partitioning that are generally there are, the first one is fdisk. Right, this fdisk that is there, this is a CLI tool, and it does not support GPT, right? So it is CLI based and doesn't support GPT. Right, so this is the first tool that you can use, fdisk. The second tool that you can use is called parted, the one that I used on my system right now. Right, again this is a CLI based tool. It supports both MBR and GPT. Right, so that is the second tool. The third tool that is there is gparted. You can install it in your system. This is GUI based version of parted. So this is just the GUI based version of parted, right? And the fourth one that we have is called the gdisk. Again CLI based, doesn't support MBR. Right, so fdisk doesn't support GPT, this gdisk doesn't support MBR, right? This parted is a CLI tool that supports both MBR as well as GPT. So this is like the recommended tool that you should always use, and if you want a GUI version of it, then you can go with gparted. I have gparted installed in my system, right? And obviously it's going to ask for my password because it is going to perform some sensitive things. But here I can see that I can simply select which one do I want to go to out of the two, the NVMe 0 and 1 or NVMe 1 and 1, right? If I go to this one, I can see like what is the breakdown of this, right? And if I go to the other one, I can see that about this first half has been unallocated in my system, and then the rest is occupied by ext4 file system, right? So I can do whatever I want through this. I can create more partitions, I can allocate this one to some file system. Whatever I want to do, I can do from here, right? So these are the general tools for partitioning. Now there is a file known as /etc/fstab, right? So there is a file known as /etc/fstab. I'm simply going to open that. Right, I'm simply going to cat that, So when I cat that, I can see that it again shows me a lot of things that are there, right? And when you want to automatically mount a file system on startup of the system, right, when you automatically want to mount a file system on the startup of your system, you can add it inside this file, inside the /etc/fstab file, right? And you cannot read or go through a file system without mounting it to the system, right? So if let's say I'm currently using Linux, it is mounted in the system. Right, we saw that folder /mnt, right, if you remember. So this /mnt, that is the folder that has my current operating system mounted into it, right? So here I can see that I have this NVMe 1N1P1 mounted, right, which is my ext4 file system, and I have my NVMe 0N1P1, which is my VFAT system, the Windows, right? So I can see that both of my file systems that I want, mounted on the startup of this system that I want to, read and go through, both the file systems are added into this file. Now it has some data points, right? It has a UUID, a unique identifier for the file, right? Like for the file system, this is the unique identifier for the file system. Now I have the directory to which the file system is mounted to as the second one. I know my root directory is slash, and this slash, this root directory is the one my Linux file system has mounted to. Everything I want to access starts from here, right? In case of Windows, it is /boot/EFI, right? So that is the like the mounting directory of my file system. Then I have the file system type itself, right? In Linux case it is ext4, in Windows it is VF80. Then I have some mount options, right? Some mount options, like there could be various mount options. You don't really have to go into that, but we have some mount options under the options. Then we have a dump and a pass. This dump is used by the dump utility to just know when to create a backup, and the default value of it is going to be 0. You don't have to change that. This pass simply means that in what order should your file system be checked in case of any discrepancies, right? So a value of 0 means that this file system will not be checked, but a value of 1 means that this file system needs to be checked at the priority of 1. So whenever I open Linux, it is going to check this file system at the priority of 1. Whenever I am going to open Windows, it is going to check the file system at the priority of 1, right? So this is the /etc/fstab file. Now we have been hearing about, or reading about this word known as swap, right? So the swap file that is there, and this word swap, right, we have been hearing about it quite a lot. So what is exactly this swap, right? So swap can be used to assign some virtual memory to your system. Now if you are low on memory, if let's say you have very low RAM or something like that, if you are low on memory, then you can create a swap partition. The system uses this partition, this swap partition. It uses this partition to swap pieces of memory of idle processes to the disk, right? So it will take out some pieces of memory that some idle processes might be occupying in the RAM. It will take that out and save it into this swap partition inside the disk. So that what it would result in is that it would free up some of your memory from your system, and that memory can then then be used by some active processes, right? Because we know a lot of processes are running in the background in the system. They might be consuming some resources out of our system, right? And since they are not so essential at the moment, they are running in the background, might not be doing anything at all, some pieces of their memory can be taken out. They can be saved in the swap partition on the disk, right? And it will save up some memory in the RAM, and that RAM can then be used for some other active processes that are actually running on the system, that are working on the system, right? Now there is one more command. I'll first clear this. So there is one more command known as df and then -h, right? I press enter. It simply shows me the utilization of the currently mounted file systems that are there. The -h flag that I've added on the command, it simply gives me a human readable form of that. So I can see for my Linux that I have currently 229 GB in size, out of which I am currently using 21 GB. I have 197 GB available, and 10% of it is what I'm using, which is currently mounted on the root directory. Right, this file system, the entire Linux file system is mounted on the root directory. Right, so this is the usual command, df-h, which can actually tell you the utilization of different file systems on your device that are mounted on your device right now. Now if you want to see what is taking how much space in your system, right, then there is another command for that, which is the disk usage. So for disk utilization, I can simply do a du and then -h, right. I press enter. This is the result that I get. It shows me the size that everything is taking. It says that the current directory overall, like the dot is the current directory, right. So the dot is currently taking, the current directory is taking total of 3.5 GB of space disk utilization that it is doing, right, entirely. And if I do the same thing for du-h and then slash and I press enter, then this is going to be quite huge. I mean the output of it, since it is recursively now taking all the directories and all the files and then giving me the result. And I can see that the total utilization of the slash itself, or the root directory itself, is 25 GB, out of which home is taking about 3.5 GB, right. And something like that. So you can just see the entire disk utilization of your system through the du command. Now let's come back a bit, right. Earlier we discussed about something that are known as inode and an inode table, right. So what exactly is an inode? And this is like one of the most important things, right. So pay attention. This is an index node. So as we already talked about, inode tables are just like a database to manage files, right. In this table, each file or a directory has something called as an inode, and it generally describes all the information about a file. Things like file type, owner, group, permissions, some timestamps, how many hard links are there to, let's say, a particular file or a directory, size of it, number of blocks allocated to it, also the pointers to the data blocks of the file, right. And this is very important. So it generally contains everything except for the file name and the file itself, right, because file is stored in the disk, right. It's not stored in the inode table, and it also doesn't holds the name of the file or the directory. Now when a file system is created, some space for inodes is allocated as well. There is an algorithm to determine how much inode space would be needed based on the size of the disk and things like that, right. Sometimes in very rare, extremely rare situations, we might see an error that you are out of disk space, right. And when you try to check how much space do I have left in the system, then you would notice that you still have a lot of space left in the system, but the system still says that there is no space left. So what it means is that your disk has space, but the inode table, or the space that was allocated for inodes, that does not has any space anymore. You can run out of inodes too, and then also you won't be able to create files. Data storage basically on our disks depend on both the data as well as the database, which is the inode table or the inodes, right. There is a command to know how much inodes are left, and that simple command, I'll just clear this. So that simple command is df, which is disk free, right, and then -i, right. So if I press enter here, I can see that in my Linux system, which is NVMe 1N1 P1, right, this is my Linux system, I can see that I have a total of these many number of inodes available, right, about 15.26 million, right? And it says that I've just used about 318k out of it, and I have about these many free, and I've just utilized about 3% of the inodes that I have, right? So earlier when I did the df, hyphen h, right, it showed me that I have used about 10% of the storage of my disk, right? But I have only utilized about 3% of the inodes, so I can still create these many number of files and directories, right? But let's say I create these many number of files and directories, and all of those files and directories are empty. Then what would happen is that it will not utilize a lot of disk space, which is this space in GBs, right? It will not utilize a lot of space, right? But since it will fill up the inode table and this number would become 0, you would still notice that here, your usage might go up to 11%, 12%, whatever it is. You will still have a lot of space, 85% plus space available in your system, but still you won't be able to create files or directories anymore, right? So the reason is that this inode number that is there is going to fill up, right? And there would be no space left in the inode table to add more entries for any new files or directories that may get created, right? So that's as simple as that. Now inodes are identified by numbers, and whenever a new file or directory gets created, they get assigned to an inode number. These inode numbers are usually in sequential order, but sometimes you may get a lower inode number because when you delete a file or a directory, the inode number that was associated to that file or directory would free up, right? And when you create a new file or a directory, it will give this number that was freed up, it will assign this inode number to the new file or directory that was created, right? So like, just to give you a very small example, right, let's say I created a file called A, right, I created a file called B, and I created a file yeah, I created a file called C, right? And let's say I delete the B file, right? So this inode number is now free, right? Now when I want to create a new file called D, right, this D will be automatically assigned to this 2, right, with inode number, because this number now got free. So this D was assigned a lower number than the last file, right? Because this got deleted and this inode got free, right? This 2 inode got free, right? And since this got free, when I create a new file or a directory, this is the inode number that is getting assigned to this new file or the directory. Now if you want to check what inode numbers are assigned to any of the files, I'll again clear this. I can do a simple ls, which is for list. I can do a hyphen l, right, which is for a long list, a detailed list, and I can add an I after that. This I means that I want to see the inode number as well. I press enter, and I can see that instead of having permissions as my first column, I now have permissions as my second column. And this number here that is there, this is simply the inode number of these directories, right? All these directories have an inode number, and this first column now is the inode number of all of these directories. If let's say there were some files, if let's say I go to bootcamp, right, and again do ls and then hyphen li, it doesn't have anything right now. I create a file test, right, and I do an lsli, I can see that this is the inode number that is assigned to this file, right? So that's how you can check what whatever number is assigned, whatever inode number is assigned to whatever directory or file, you can simply check it through an ls hyphen li. Now you can also get a more detailed information about anything through a command known as stat, right? So I can do a stat and then I can write bootcamp, I press enter, and I can see that I've got a very detailed information about it. I got its size, its block, its IO block, right, its type, which is a directory, the device, right, the inode number, how many links does it have, right, then the access, the UID, the group ID, right, and some timestamps, right, timestamps for access, timestamps for modification, timestamps for change, right, and the birth, as in when was this file created, right? So this directory was created on 13th May 2022, right? So all of these things I can see a very detailed view of the bootcamp directory, right? So that's how I can see that. Now there is one very interesting question: how does an inode locate a file? Now we know that our data is somewhere in the disk, and probably it wasn't stored in a sequential manner, and I'll give you a very good example of that, right? So just like be with me here, right? Let's say I create a file known as first name, right? And I create a file, another file known as last name, right? So let's say I have these two files, and let's say that this is the storage that I have, the total storage that I have, right? So let's say that I create this first name and file, right? And I add one name into this, Apoorv, right? This is the very first thing that I added, right? So I know that this Apoorv is going to get stored here, right? Now let's say that I add a last name here, right? This is the second value that I am entering, and I add my last name here, which is Goel, right? I know that this second name is going to be stored here, right? Now let's say I add another value here, which is the third value that I am entering, and the name I am entering is Kunal, right? So I know that my third value is going to be entered here, and let's say that I add a fourth value here, which is Kunal's surname, Kushwaha, right? I know that this fourth value is going to be stored here, right? So now I know that this 1 and this 3 belongs to first name, right? And I also know that this second and fourth belongs to the last name, right? So although this 1 and 3 belongs to the first name value, like this first name file that I created, although these two data points belong to the same file, they are still stored in different, blocks. They are not stored sequentially here, right? And for the last name, I know that these and this belongs to the same file, but again it is not stored sequentially, right? So I know that my data is somewhere in the disk, right? But I don't know exactly where it is, and probably it wasn't stored in a sequential manner. So to find all that data, I need to use inodes here. Inodes point to the actual data blocks of that file, right? So this file's inode is going to point me directly to this 1 and this 3, and this file's last name, this first name's inode, is going to be directly pointing me towards 1 and 3 in the memory, right? And this last name's inode, they are going to be pointing me directly towards this and this. Now typically in a file system, and not all file systems work in the same way, but typically in a file system, each and every inode contains 15 pointers, right? So each and every inode is going to contain 15 pointers, right? I'll just quickly draw this one thing. Don't mind my handwriting, right? So it has these 15 pointers, right? 1 2 3, and then up till 12, and then 13, and then 14, and then 15. So I know that it is going to contain these 15 pointers. Typically in any file system they are going to be there, right? 15 pointers, These 15 pointers are like, this entire thing is also known as a super block, right? And super blocks are something that we talked about earlier, right? So after the boot block there is a super block, right? And after that there is the inode table, right? So each and every inode is going to have this, 15 pointers, which is also known as a super block, right? And these blocks have a size of about 4 KB, right? And the first 12 pointers, the first 12 pointers that are going to be there, they are going to directly point towards the data blocks of the file to which this inode belongs to, right? So they are going to point exactly towards 1, they are going to point exactly towards 3, and for the second file, for the first file they are going to point exactly towards 1 and 3. For the last file they are going to point exactly towards 2 and 4, right? But since these blocks are usually 4 KB in size, does that mean that any inode can just contain 48 KB of data max? That's not the case. That's when the 13th block comes into picture, right? So with the 13th block, what this does is it usually points to another group of pointers, right? It contains another group of pointers. Let's say that this is the data, right? The data as in like what we were talking about here. This first name is a data file, this last name contains some data, it is a file, right? So let's say this is the data here, right? Now these first 12 pointers are going to point directly towards data, right? This 13th pointer is going to point towards an array of pointers, right? That is going to point towards data wherever it is stored in the memory. Now this 14th is going to again point towards an array of pointers that again points towards an array of pointers that are going to point toward data, and this 15th again points towards some data, right? Which again points towards some data, which again points towards some data, and all of these are going to again points towards data. So that is why, if you remember, that when we talk about the ext4 file system, right, it can have about 1 EB or 1 exabyte of disk size, right? It can have about 1 EB of disk size, but it can have a file size of 16 terabytes, right? So this 16 terabytes of file size, the maximum file size that it can have, forms through these inodes, right? All these inodes that are there, right? The inodes that point towards an array of inodes, or the inodes that points directly towards the data and things like that. All of these inodes, the entire size, that the maximum size that they can have, like contain with smaller blocks of 4 KB each, right? The maximum size that they can contain for a data is 16 TB, right? For the ext4 file system, right? So that's how inodes usually locate data in a disk. They have the first 12 pointers that are pointing directly towards the data. Then the 13th pointer that is there is pointing towards an array of pointers, right? And this array of pointers is going to point toward the data. And then this 14th, is going to have an array of pointers, which is again going to have some point towards some array of pointers, which is going to have this data. And this 15th is again going to have an array of pointers, right? Point towards an array of pointers, which are going to point towards some array of pointers, which are going to point towards some more array of pointers, and they are going to point towards the data. So the bigger the data is, the more, array of pointers are going to point towards that data, and they are, all linked to this 15 super blocks, right? And this kind of mechanism is generally created so that, the inodes form some consistency, right? So again, I mean, when we talk about this, you know array of pointers, when I talk about, let's say, this array of pointers, then this is again going to have a similar structure of 12, uh, these 12 pointers that point directly towards the data, then a 13th pointer, a 14th pointer, and a 15th pointer, right? These pointers, these arrays of pointers are again going to have this similar structure. First 12 pointers pointing directly towards the data, then a 13th pointer, then a 14th pointer, then a 15th pointer, and then these pointers from the 15th pointer of the first, super block that we had are again going to have a similar structure with the, you know 12 blocks of that directly points towards the data, then the 13th pointer, 14th pointer, and the 15th pointer. So they all follow the same structure, right? They all would always follow the same structure, but this is how it usually is, right? And this is how it knows exactly how to locate the data, usually no matter how big it is, because 16 TB of a single file or a directory is something difficult to have, but for a normal use case. But yeah, I mean, this is usually how it works. Now one more thing that is there is that all these blocks that are there, all of these blocks, right, they are known as indirect blocks. Indirect blocks because all of these blocks are pointing indirectly towards the data. So this 13th block is, if we talk about this 13th block, is pointing towards, this one, right? And then this block is pointing towards the data, this 14th is pointing towards this, right? And this is pointing towards this, and then this is pointing toward the data, right? This 15th is pointing towards this, and then then it is pointing towards this, and then this is pointing towards data, right? So all of these are known as indirect blocks. So this is how inodes usually know where to locate a file. And since, I mean, files are stored, in an insequential manner, just how I showed you in this example, then it is not easy to locate a file. But just because, inodes have all these pointers to, point directly towards the file, and some indirect blocks that are pointing towards the file, that's why, I mean, inodes are easily able to locate a file in a file system. Now before we conclude this video, let's just quickly talk about one last topic, right? I'll quickly scroll down. Let's just talk about one last topic, which is known as symlinks. Right. So in Windows, we know that we, like, all of us are familiar with shortcuts, right? We can have a shortcut of any directory, we can have a shortcut of any application on our, desktop. Whenever we try to install something, it asks us, do you want a shortcut on the desktop as well, right? So shortcuts are what? They are simply just aliases, right? They are simply just aliases. Right, they are just simply the alias of the directory or the program, whichever we are shortcutting in the desktop, right? Now if you do something with the original file, if you, let's say, delete the original file, you delete the original directory, you make some changes, it is going to affect the shortcut as well, might break the shortcut as well, right? Because if, let's say, the original file does not exist, then what is the shortcut going to lead to, right? So it may also, break the file sometimes. Now in Linux, these symlinks, or also known as symbolic links, they are equal to shortcuts, right? So these symbolic links or these symlinks are simply just shortcuts in Windows. Now to show you an example, let's do something on the command line, right? I'll clear this up, right? and I'll go to the bootcamp directory, remove this test, right. I'll simply do an echo and I'll send it to the test1 directory, right. Again I'll create a test2 and send it to test2. Again I'll create a test3 and send it to test3, right. If I do an ls here or ls-l here, I can see that I have these three files created here, right. Again let me clear this and do a ls-l, right. Now let's say I want to create a symbolic link or a symlink, a soft link, right. These are the three names by which it is known: symlink, symbolic link and soft link, right. So let's say I want to create a soft link here, so I can simply do ln, which is for link. I can do a -s, which means soft. I want a soft link, right. And then I can do a test1, right, that I want a link for test1, and I want to name is as soft1, right. This is what I want to do. I press enter here. Now again let's say I do a ls-l here. Now this time I can see that these soft links, I mean I already had these three files created, but now I have another file here, right, which is starting with an L. So this type bit is L here, which means link, right. And it created a link called soft1, which is pointing towards test1, right, because I linked test1 to soft1. Now as you can see, symbolic links or soft links, they usually points towards the file, the name of the file to which they are linked, right. Now similarly, there is something known as a hard link as well, right. So there is something known as a hard link, and to create a hard link, what I can do is I can simply do a ln and then simply just test2 and then soft2 or hard2, right. I press enter here. Again I do an ls and then -l. I press enter. I can see that a new this thing is created, and the name is hard2, right. And I can see that this is not pointing towards anything here, right. It is not pointing towards anything here, right. Now do you notice any changes like from this one and this one, except for one more hard to created? Do you notice any changes as such? Just observe it. Now one change that you would notice is that this column, here in test2, this says 2 right now, and earlier it was saying 1, right. Here it was simply saying 1, this, right, but this time it is saying 2, and the new file that we created, hard2, also says 2. So this second column that we have been like wondering about from very long, right, this means that how many hard links actually exist for a particular file or a directory, right. So since I created a hard link here, earlier it said that it has no hard links, right. So it says 1, right. But now since I created a hard link here, it says 2 here, right. And if I let's say do an ls and then li and I press enter, I would notice that the inode number of this and the inode number of this is same, right. I can even search this up with a control shift and F. I simply just copy this, I paste it here, right, and I can see that these two are exactly same, right. The one that I just created and the one that I already had, test2 and hard2 have the same inode number, right. But we said that each and every file or directory that we create should have a unique inode number, right. The inode number cannot be shared between two, right. So that's what usually links do, right. Now going back to the screen here, let's say that this is my inode number, right? And let's say that this is a file that points towards an inode number, right? And now let's say I create a soft link, right? I created a soft link here. So I created a soft link here. Now this soft link, instead of referencing directly, instead of pointing directly towards the inode number, right, it is pointing towards the file name. But on the other hand, if I create a hard link, right, which is a hard link of this file only, right, if I create a hard link, then this is pointing directly towards the inode, right? So if let's say this file gets deleted, let's say if this file got deleted, right, this soft link would also stop working, right? But since this hard link that I created for this file, since this hard link that I created for this file is pointing directly towards inode, right, then this file would still work. If anything happens to this file would still work. And I'm not saying that if you make any changes to this file, then they won't be reflected. They would definitely be reflected. If you make any changes to the original file that is there, it is going to be reflected in the soft link. It is going to be reflected in the hard link as well. But if you delete this, if you delete this file itself, then the soft link is not going to work anymore, but the hard link would still work, only reason being that it is directly pointing towards the inode, right? Now I have one question for you, and I am not going to answer that question in this video. If you, let's say, make any changes to the soft link file, would that affect the original file? And another question, if you make any changes to the hard linked file, would that make any changes to the soft link file? You can try to do that. You know a lot of commands, you know how gedit works, you know how to create soft links, you know how to create hard links now, right? For soft links I simply added a flag, that was -s, which meant soft. But when I was creating a hard link, I didn't mention any flag. I just did an ln and then test2 and hard2, right? So just try to find answer to this question. If you make some changes to the soft link file, would it affect the original file? If you make any changes to the hard link file, would it affect the the original file? And if you delete this file itself, the original file, just try to see if this file still works or not, and just try to see if this file still works or not, right? As simple as that. Very simple activity, but try to do that. You already know a lot of commands. I think you would be able to do it. I'm not going to let me know the answer of it in the comment section below, right? Because we need to increase the engagement of this channel, right? So let me know the answer to whatever you find out of this question in the comment section below. And with this, I think that's pretty much it for this video. And we've covered about file systems and devices in quite a lot of details, right? And I don't think there's anything else that you should know about in detail as of this point of time. So we'll conclude this video. And again, talking about the Learn in Public initiative, just make sure that whatever you learned out of this video, write a nice Twitter thread about it, or write a blog on Hashnode or Medium or dev.to, any of those platforms. Just write a nice blog about it, right? Like, post about it on Twitter, share it with me, right? Use the hashtag learning with Apoorv, right? And just let me know in the comment section below the answer to this question, as well as if this video was easy to understand, because this was definitely not easy to explain, this was definitely not easy to shoot, but we did it, right? Don't forget the Learn in Public initiative. It is going to help you immensely in your career, right? So let's be serious about that, right? And the best blogs and threads that I'm going to receive with the hashtag learning with Apoorv are going to be featured in the virtual tech school's website also. So you're going to get some reach out of that. And don't forget to mention me in those tweets. Apoorv tweets is going to be the tweet. And yeah, I think that's pretty much it for this video. And I'll see you in the next one. Till then, peace.